Okay, so we're going to start the course with a bit of a review, hopefully, for all of you. The We're going to be using vectors a lot in the course, okay? Um, and just as kind of a refresher, and maybe even I'm going to point out some things that didn't really even occur to me until much later in college or even after I was a practicing engineer. Um, that helps. You know what I mean? So um, let's start off with sort of the basics here. So what is a vector? For our purposes, a vector is a quantity with both a magnitude and direction. Okay. Um, so some examples. There's so the position. There's a position vector where the magnitude would be the distance from a reference point or the origin, and obviously the direction. So um, velocity. Let's see, acceleration. These are kind of the big um, the ones that we're going to be using in this course. The position and its derivatives essentially, and then you have a force and maybe momentum. Um, those are some examples of a vector, and it's often vectors are often um, represented with an arrow, where the length of the arrow would be the magnitude, and so this is the vector A, the symbol, so this is a vector A, and I'll explain this here in a second. So A, the vector A, um, uh, or I said, so sort of a note on notation, the magnitude of A in this case is represented by just the bare letter. Okay, the vector itself gets the arrow on top. So uh, this is equal to, and sometimes I'll explicitly have to describe the magnitude this way. So if I have a vector inside of these vertical bars, that means the magnitude. So it's represented either with the letter without the arrow, or if I have a vector and I want to apply the magnitude operation to it, then that's what these vertical bars are. Sometimes called the norm. So the direction is given by a unit vector. Unit vectors get this special notation with the little caret hat thing on top. And so what that is it's a vector, it's another vector in the direction of the original vector, but with with a magnitude 1. So this is called a unit vector. So any vector with a magnitude of 1 is called a unit vector. Okay, and so to sort of drive the point home, the magnitude of the unit vector is equal to 1. Okay, so all right, so now we have this quantity. What can we do with it? Well, we can add them together. We can add vectors together. So and this is done. So if I have two vectors, A and say another vector B, then their addition, or the you add them together using this rule here. So this is A, and you basically put them the tail of B. You join the tail of B with the head of A, and the sum of those things is defined by the result, joining the tip, or I'm sorry, the tail of A and to the tip of B in this case. Okay. Similarly, we can do a thing called scalar multiplication. And a scalar is just a number. So, for instance, 2A is just equal to A plus A, which is just following the same logic. It'll be, so if this is A, I join another A, and so the result of 2A would be, just like it is here, would be this vector. So this is A, this is A, and this would be 2A. Now, there's this clear definition, and when you're multiplying by an integer, right? You have this understanding, but this is, you can, I'm sorry, it expands just the same way multiplying by fractions that does with numbers, in that say 0.5a is just if this is the original a, it would just be the original a but half the length. So you can multiply by 0.5 and you would get the same vector except shortened by a factor of a half. Okay? Okay, so we can use these two principles to bring this geographic, or I'm sorry, not geographic, but oh man, this geometric interpretation into the realm of, numeric analysis, I guess, is maybe that's the right word for it, but we can bring it into math of numbers and things like that. So we can expand A in terms of a set of basis vectors, and the most popular ones, the ones that are most commonly used, are called the Cartesian coordinates. And so if everybody should be somewhat familiar with the Cartesian setup here, but so if I have 3 coordinate axes of x, y, and z, then I can define basis vectors in that direction. So here's I. It's helpful that they be unit vectors, j and k. So this is the most common setup, right? So if I have a vector if I have a vector A, then I can define it in terms of a sum of a scalar, a product of the, a sum of the individual unit vectors that we've defined here. Okay, a scaled, I guess a scaled product, or the weighted product of those, or weighted sum of those three basis vectors. So we can expand A in terms of the x component, which multiplies the I. So in this case, it would be, anyway, times a y component, which multiplies the j vector, and a z component, which multiplies the k vector. This is a typical setup, okay? And so in this setup, we can define vector addition simply by adding the components. So okay. And then likewise for scalar multiplication, say if I want 2 times a, that's just going to be 2 times ax plus multiplied by I, plus 2 times ay multiplied by j, and same for the z coordinate. Okay. All right. So now what can we do with vectors besides just add them and multiply them by scalars? Well, we can multiply them with one another, and because we have a couple different ways to do that, actually. So we have the first one, which results in a scalar. This is called the dot product. Some people call it the scalar product. There's all kinds of different names for a lot of this stuff, but we're going to call it the dot product, and it's annotated with a dot. Okay, and so the operation of the dot product gives this quantity. The magnitude of A times the magnitude of B times the cosine of the angle between them. So if I have two angles, or I'm sorry, if I have two vectors A and B, they have an angle between them, and A dot B is given by it results in a number. So I have two vectors go as the input. The output is a number. It's simply a number. Okay. In Cartesian coordinates, it has this simple representation, or a simple formula for calculating it. So A dot B in Cartesian coordinates is given by the sum of the product of the individual components. So we have multiply the x components, multiply the y components, and multiply the z components. Add them up, and that gives you A dot B. Okay. This is kind of the more fundamental definition, because it's true even when we're not in Cartesian coordinates. But Cartesian coordinates do give us this simple way of calculating, which is useful. Now let's expand on this a little bit. So there's a couple of special circumstances. So what if we're given the situation where A dot B, or A and B, are perpendicular to one another? Okay, then A dot B in this case is equal to the the product of the magnitudes and the cosine of 90 degrees, or pi over 4, pi over 2, which is 0. So perpendicular vectors have 0. The dot product of perpendicular vectors gives 0. Now that's useful. Sometimes it's going to be useful for us to find special vectors which are perpendicular. So this little formula here is useful in that case. And also, if theta could be greater than 90 degrees, so in that case, so if we have something like this, so A is over here, so in this case, A dot B is, I guess, is less than 0. It gives a negative number. So that's when theta is greater than 90 degrees. Okay. All right, so properties of the dot product. It's commutative. Which means that A dot B is equal to B dot A. And distributive. Meaning that if I have A dotted with the sum of B and C, that is equal to A dot B plus A dot C. And likewise, scalar multiplication has a sort of a trivial expansion of this. So if I have a scalar m and I multiply it by the dot product of A and B, that is equal to I could multiply by the first. I could multiply the scalar by A first and then take the dot product, or I could multiply it by I can multiply B by the scalar and then take the dot product. Or I could take the dot product first and then multiply by the scalar, and they all give the same answer. Okay. So this is useful for doing things. I mean, it's useful for a lot of different reasons. Like it defines certain quantities, or it helps define certain quantities, I guess. But one very useful purpose for the dot product is what's called projection. So sometimes it's useful, like say rather than decomposing A, rather than composing it in terms of the Cartesian coordinates, the standard basis vectors of I, J, and K, maybe I want to know how much of A is in the direction of B. Or if I want to, this is going to be useful to define A in terms of other vectors, or A vector in terms of other vectors. So if I have two vectors, we'll just stick with A and B, I guess. That's a bad example. Say I have So rather than defining A, I could define A in terms of its Cartesian coordinates, which would be just like we've already written, the component AX times I, and so on. I could also define this in terms of the vector B. So maybe I want to know how much of A is in the direction of B, which would be like that. So maybe I'll call that A in the direction of B. And then there's going to be a remainder, which would be A perpendicular to B. You know, there'll be like a, once I could, so rather than defining it this way, I could also define it as A in the direction of B times a unit vector in the direction of B, and and then whatever is left over. So it'd just be A perpendicular to B. So I know A, I know B. So oftentimes you won't know this. So maybe this offers a convenient way or an easy way of determining how much of A is perpendicular to B. Okay, and so to do this, this component AB is literally just A dotted with the unit vector in the direction of B. Where to find the unit vector in the direction of B, that is just the vector B divided by its magnitude, right? So if I take 1 over the magnitude, or the inverse of the magnitude, and I multiply it by this vector, just from what we've done here, we've shrunk the length by 1 over the magnitude, right? So this is equal to, I mean, it's kind of a trivial thing, so you guys can see what's going on here. If I multiply it by the inverse of the magnitude, the magnitude of this becomes 1. So now I have a unit vector in the direction of B. All right. So oftentimes the thing you're looking for in this case might be the perpendicular vector, and that's just going to be the original vector minus the portion of it, or I guess it would be, maybe to expand the formula completely, it would be A dot B times the unit vector in the direction of B. Okay, so if I want to know how much of a vector is perpendicular to the, to some other vector, it's going to wind up being a useful thing to do. Take my word for it for now. Okay, so besides the dot product, there's in 3 dimensions, and we kind of cheat and use them in 2 dimensions as well. There's another product called the cross product. Okay, the cross product is symbolized with, the cross, simple X. This is, so if I have 2 vectors, this gives a third vector. So if I have a vector A and a vector B, and they have an angle between them of theta, using what's called the right-hand rule, C, which would be the cross product of A and B, is given by it's the vector that's mutually perpendicular to both A and B. So C is perpendicular to A and B. Okay, and its magnitude is equal to A, the product of the magnitudes times the sine of the angle between them, rather than the cosine. All right, and it's like I said before, its direction is determined by the right-hand rule. So if you take your right hand, you go, A cross B, so I go through A, around through B, and C will be pointing in the direction of my thumb. It's the right-hand rule. Okay. In Cartesian coordinates, there's a simple little way for computing it. It's given by the determinant of this strange matrix here. So I put the unit vectors at the top. So this is basically just a way of computing the cross product. I don't know that this determinant really doesn't make that much sense in terms of actual matrices, but it's calculated the same way. So, and then I have to have the components of the first vector, in this case x, y, and z, and then the components of the second vector. And I take the determinant of this matrix, and so that's given by, so if you remember from calculus, eliminate the, or if you've done any linear algebra, at some point in your life you've hopefully have seen this. So you eliminate the row and the column. In this case, we're choosing to eliminate the first. We're going to expand it in terms of the first row. So you get, and you take the product AYBZ minus AZBY. Okay, now we subtract, we alternate signs. So first we're starting off with positive, and then we subtract the j component, and so we eliminate this row and this column, and it's take the product of what's left, the 2 by 2 matrix that's left. So AX, or the determinant of the 2 by 2 matrix that's left, AXBZ minus AZBX. And you kind of notice like the components that aren't, so if we're computing the y component, if we're computing the y component of the cross product, it involves the components that aren't, that aren't the y component. So it's the x and z components. And likewise and then for k, it's the same sort of things. We eliminate the first row and the last column, in this case AXBY minus AYBX. In 2 dimensions, oftentimes if you can take the product in 2 dimensions and you'll be dealing only with AX and AY, AZ will be 0 as well as BZ will be 0. So the only component that is non-zero in that case will be the K component. So this formula here gives the cross product in 2 dimensions. I'm being a little loose with it, but the plane, the XY plane, is just a special case of 3 dimensions. So the procedure works regardless. It's just easier in 2 dimensions, I guess. All right, so the properties of the cross product are that it anti-commutes. It's anti-commutative. And that means A cross B is the negative of B cross A. And that's clear. So if I were going to do B cross A, I would start at B, get through A, and my thumb would be pointing in the opposite direction. So A cross B is I go through A to B, and I'm pointing up. I start at B. If for B cross A, I start at B, cross through A, and I'm pointing in the opposite direction. It's still mutually perpendicular, but just in the exact opposite direction. Okay, and every other property is kind of the same as the dot product. So it's distributive, meaning as well as the trivial case with the scalar multiplication. So scalar A multiplied by the cross product of A and B, I'm sorry, the scalar M is the same as, so you can multiply A by the scalar and then take the cross product with B, or you can multiply B by the scalar and then take the cross product. Or you could take the cross product first, and they all give the same answer. And that follows directly from the definition. One last thing almost forgot to cover was, how do we calculate the magnitude of a vector? So we've used it in several places, but we never went over exactly how to calculate it yet. So the magnitude to find the magnitude of a vector, there's a couple. Essentially, it turns into just an application of the Pythagorean theorem. But in terms of these other vector properties, the magnitude is the square root of the dot product between a vector and itself. Okay. Now, why is that? So, just using our formula, or the definition of the dot product, A dot A is going to be the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, right? So what's the angle between a vector and itself? Is going to be 0. So cosine of this just comes out to a squared. So if I have the two vectors, if I take the square root of this, if I take the square root of the dot product of the vector with itself, I get a, right? So the square root of a dot a just gives the magnitude. All right. In Cartesian coordinates, this just comes out to be, the square of the sum of the square of the individual coordinates. The square root of the sum of the squares of the individual coordinates. Okay. So, just to be explicit here. And then in the special case of Cartesian coordinates, we can just take the individual components and square them, add them up, take the square root, and that's what we get.